Journal for Resilient Cities and Structures Academic Forum. Today, we are very honored to invite Professor Machine Beer to give us a presentation. My name is Yin Zhou. On behalf of the journal, I would like to introduce Professor Beer first. Professor Machine Beer is the professor and head of the Institute for Risk and Reliability, Leibniz University, Hanover, Germany. He's also part-time professor at the University of Liverpool and guest professor at Tongji University and Tsinghua University, China. Dr. Beer's research is focused on uncertainty quantification in engineering with emphasis on imprecise probabilities. He is editor-in-chief of the ASME Journal of Risk and Uncertainty in Engineering Systems, Part A, Civil Engineering, and Part B, Mechanical Engineering. He has won, several awards, prestigious awards, including the Alfredo N Award on Risk Analysis and Management of Civil Infrastructure of ASCE. Dr. Beer is the chairman of the European Safety and Reliability Association, ESRA, and a co-chair of Risk and Resilience Measurement Committee, Infrastructure Resilience Division, ASCE. Okay, so please join me to warmly welcome Professor Beer to give us a presentation. Thank you.
So, Professor Zhou, thank you very much for your kind introduction, and very warm welcome to everybody watching the presentation. So, first of all, I would like to draw your attention to the journal Resilient Cities and Structures, which I think is a fantastic platform to publish our research on resilience, in particular related to infrastructure systems. And that is also what I would like to talk about today, very much related to the topic of the journal. I would like to talk about resilience of complex infrastructure systems and how we can address this. So this means that this presentation is not very much in depth in terms of technical detail. It is more focused on the concept behind how we can address resilience of complex infrastructure systems, because infrastructure systems are complex systems, and that means that we have quite some issues to solve if we want to talk about the resilience of these systems. So that means if we are talking about complex systems, we go one step back and say, what is a complex system? And a complex system can be actually anything. That can be an infrastructure system, but it can also be anything else. It can be a wind farm, it can be a hydropower plant, it can be a log shifting ships, it can be Internet of Things, it can be machinery like aircraft turbine, it can also be human body. So the problem is that if we want to make decisions on, let's say, improving the performance of such a complex system, or bringing back such kind of system to its service after some disruptive event, then we need to think about how we can assess this in a quick way and in a reasonable way. So that means we need to understand how the system behaves, and we need to understand how we can bring it back to service if we have some disruptive event. So that means we need a model for our system which is capable of giving us basically the key features or the key important information on our system in relation to what happened and what needs to be done. So when we think about the modeling of these complex systems, that means if we want to model such a system in a physical way, we need a lot of detail, and we need a lot of information, and we need a lot of data. Usually, we don't have all this kind of information available, but only to some extent. So the more we want to model in detail, the more information we need, which is actually not really available. That means we can only model these complex systems up to a certain degree, and the rest is uncertainty related to risk. Now we need to find a kind of balance between how much we can afford and how much is available in form of data and information about the model and the system, and how much do we need in order to make some decision. And that is kind of balance that we need to consider if we want to make decisions. So the question is, what do we need to make decisions in relation to the performance of such complex systems? What we need is reliable information. Reliable information, of course, on the system performance and failure risk. And that information needs to give us a or that information needs to be reliable in the way that we need to be able to trust this information. This cannot be just a guess or something like this. The second item is that this information needs to come to a sufficient extent. Partial information at very low extent is not helpful, because this doesn't give us a complete picture about the performance of our system. So we need this reliable information also to some sufficient extent. The third point is that we need this information relatively quickly in order to make quick, informed decisions. So this analysis or these analysis results or information need to be available on time. So that means we need a quick analysis. So we cannot wait for a huge model to give us some answer in 3 weeks or something like that. That would be too late. We need to have this information on time. Yet the information as a basis for making decisions needs to cover all relevant aspects. It's not sufficient to, let's say, look at only one aspect. We need to cover all the relevant aspects, in particular in relation to resilience. When we are talking about infrastructure systems, that means we should not only cover all the very technical details of the system, we also need to look at the environment. We need to look at even societal aspects. We need to look at economic aspects and these things. So that means we need to look at the problem in a kind of broader perspective. So that now sounds like a task which is a bit unrealistic, but somehow for practical purpose, we need to solve it. So how can we address it? So the concept can now be the following. We need an appropriate systems model which covers all the uncertainties, because the uncertainties are in balance to the model detailedness. Less detail in the model means more uncertainties, but we need to cover these uncertainties and not believe that a rough model will give us a precise answer. We need to assess also the quality of this model response if we are dealing with a rough model. The second point is we need a highly efficient analysis technology to deliver information on time. And we need a multi-criteria and multidisciplinary approach to cover all the relevant aspects. So that means we need to combine the very technical details with also some economics, environmental, and so forth, other aspects. So how can we now do this? The systems model can be based on functionality instead of technical details. So what does this mean? We want to set up a model not based on the very physical features of our problem, but we just look at the functionality. We need to look at input-output dependencies, which are important for decision-making and which cover the key aspects which basically drive our system. So that means we need to look at, or we can look at much less detail, just looking at really the key features of our system. And of course, that needs to be connected to real data. The second item is the quantification of the uncertainties. So here we have to consider 2 types of uncertainties, which is aleatory and epistemic. And they are related also to this kind of balance between model detailedness and uncertainty, to model our system only as precise as necessary and not as precise as possible. Because that would be a huge effort to model in very detail. And then we don't even need maybe this kind of detailed information in order to make decisions. But if we have less detail in the model, we need to cover these uncertainties. So now the aleatory uncertainties come from a physical background. We cannot influence them, but we need to quantify them. So that is variability in the system, in the loading and so forth. But the epistemic uncertainties is what we can control. That is related to a lack of information, a lack of perception and these things. So that is related to limited information. So less detail in the model means more epistemic uncertainties. More detail in the model means less epistemic uncertainties. So that can be controlled in balance between model detailedness and epistemic uncertainties. And that helps us then to come up with a compromise solution to have the optimal, let's say, detailedness to make decisions. Then for the analysis, we should go for some non-intrusive approach, which is generally applicable, which can be combined with any kind of system. So that means we should use maybe kind of sampling methods, which can be connected to all kinds of systems being non-intrusive. Otherwise, we would develop solution concepts which are only bound to some specific, very small class of problems, which would not be very helpful. We want to have something which works in general. And finally, for the multi-criteria and multidisciplinary approach, we should use some resilience-based approach for life cycle management to look at the overall system and the performance over its lifetime, also maintenance and restoring the system coming up to full performance after some disruptive events and these things. And that gives us also the opportunity to include environmental aspects, societal aspects, and economic aspects. So that is the multidisciplinary part. Let's now look at the uncertainty stuff first. So let's say we answer a typical civil engineering question: is the structure safe? And then we say, okay, of course, we can go back to some data, collect some information, put up a probabilistic model, perform a reliability analysis, and come up with a failure probability. Of course, this is the, let's say, traditional way. But what happens actually is, if we look at reality, we have epistemic uncertainty. So we don't have perfect information. We don't have information to a sufficient extent. We have limited data, and we have only a kind of blurred picture of reality. So what does this tell us? If we come up with a precise probabilistic model based on that kind of blurred picture, the question is the reliability analysis then still reliable? And what are the effects of this epistemic uncertainty on the results? Can we quantify this? Can we use this? And the answer is yes, we can. When we say, okay, based on this blurred picture, we can still come up with a set of plausible models. And if we have more epistemic uncertainty, we have a wider set of these models. So we don't actually need a precise model, but we need to translate this epistemic uncertainty also to the result, so that we reflect this epistemic uncertainty, for example, in terms of an interval of the failure probability. And if our epistemic uncertainty is very big in the input, means we have very limited information, then we can only say, okay, the failure probability is between A and B, and that interval may even be large if our epistemic uncertainty is large. So then the next point is, of course, we cannot be sure to have these precise bounds on our set. But in order to make a decision in engineering, we don't need to know these bounds exactly, but we need to know how sensitive is our result with respect to the width of the set. So we do a kind of very rough sensitivity analysis, basically play with the width of the set and see how sensitive is my result interval, for example, of the failure probability with respect to this epistemic uncertainty. And if this sensitivity is very low, then we can still make robust decisions, although we might have a lot of epistemic uncertainty. On the other hand, if we see a strong sensitivity, then we need to go back and find out more about our system, how it performs. So now we need a model, an efficient model for the systems analysis. And we found that the concept of survival signature is quite nice for this and quite powerful. So this gives us a compressed representation of system availability. So which means that if we have a system where all the components are of the same type, so being exchangeable, we can say that, okay, the system has M components and L out of M components are working. So now for L out of M components are working, we can have different arrangement of the working components in the system. In some of the configurations, the system may work, in some not. So now the number of working configurations over the total number of possible arrangements gives us a percentage of the arrangements of the components in the system for which the system is working. So that gives us basically a probability that the system works if L out of M components are working, although we don't know in which places are the working components. So simple example, let's say we have this simple system here with 1, 2, 3 components, and we say 2 out of the 3 components are working. So we have 3 different configurations possible for this. 1 and 2 are working, 1 and 3 are working, 2 and 3 are working. Of course, the system is only working in the cases 1 and 2, 1 and 3, and it's not working in the case 2 and 3. So in 2 out of the 3 cases, the system is working. So the survival signature gives us a probability of 2 over 3 that the system is working. And that can be done for 0 out of 3, 1 out of 3, up to 3 out of 3. So this concept can now be expanded to different types of components in the system say we have k component types, and for each component type, L out of M components are working. So then we can still use this kind of concept, like in this example. Say we have two types of components, 1 and 2. For type 1, we say, okay, 1 out of 3 are working, and for type 2, 2 out of 3 are working. So that means we have 9 different configurations for these working components for their distribution in the system. So in the first case, we say, okay, in first parenthesis, now consider type 1 component working, the one at the entry of the system. And then we have 3 different arrangements for component type 2. So this shows the first one working, where the system is not working. Second possible configuration for the 2 types are working, system is not working. And for the third option, the system is working. So then we jump with the working component of type 1 to the other 2 places, and then the entry of the system is dead, so the system is not working at all. So out of the 9 options, only in 1 configuration the system is working. So the probability that the system is working in this case is 1/9. So that can be done then for 2 out of 3, 3 out of 3, and so forth, so that we get the full overview of this system. So now, the nice thing of this kind of analysis is now the following. We need to do the systems analysis only once in order to get this kind of statistical statement for system is working if L out of M components are working. So this is now this phi. So this is a conditional probability, and the condition is that L out of M components are working. And this conditional probability is now controlled by the lifetime distributions of the components. Since it's a conditional probability, it can be multiplied with the survival signature to give us the survival probability of the system. So the interesting thing is that the system structure is covered in the survival signature, and the lifetime distributions are covered in the probability structure, which is now disconnected from the systems analysis. So this means we can come up with a very efficient simulation based for the lifetime of the system, which is done only on the probability structure once the system structure is solved once. Of course, we need to understand that the analysis of the system structure is a combinatorial problem. So that combinatorial problem needs an efficient solution as well. But when we look at the entries in the survival signature, we find that these numbers are not very, very small to very close to 0, not very close to 1. So they can be estimated even with crude Monte Carlo in a very efficient way. And we don't even need to evaluate all the entries in the survival signature. We only need to evaluate some, and then we can do we can have a surrogate model like a Kriging model, or we can use radial basis function neural networks and these things in order to estimate the survival signature of the system, even though we calculate the precise or the exact values only at certain points. So that can be done in a very efficient way. Further, we can then use it for complex system structures. It can be used for larger systems. It can also include all kinds of dependencies between the survival, between the lifetime distributions, because this is only covered in the probabilistic structure here in the green part, which is easy to implement. Also for the sampling then. And when we change components, we basically change only the lifetime distribution of that new component. We don't change the place where this component is located, so we don't change the survival signature, which is the system structure. So that can operate also with imprecise probabilities, even including dependabilities. So that is a very efficient method to, let's say, analyze the system in an efficient way, including all kinds of uncertainties involved. So this can be shown, for example, in this hydropower plant example here, where we say, okay, we have only a very rough model for this hydropower plant, a very large system actually, but we have a very, very rough model for this. And each component in this model, in the systems model, is actually a kind of hypercomponent. So basically, each component represents a bigger part of the whole system. Since we summarize many components in these hypercomponents, we have some uncertainty in the lifetime distribution of these hypercomponents. So that means we need to consider epistemic uncertainty in the lifetime distributions. And that can be done with intervals as parameters for the lifetime distributions of these different types of components. So here we have 6 different types of components with different types of lifetime distributions, each one covering epistemic uncertainty because of limited information and summarizing part of the system in these components. So we use these parameters as intervals. What we obtain is then a survival function which looks like this. So traditionally, we would get the red line as the survival function, so survival probability going down over time. Now we have these interval parameters in the lifetime distributions, which come up as a reflection, which are reflected in the result, coming up with this bandwidth between the dashed black line and the dotted blue line. So this range of lifetime or this range of survival functions reflects the range of epistemic uncertainty reflected in the intervals in the lifetime distributions of the components. So basically, we have model uncertainty here reflected in this range of a set of survival functions. So now the point is, if we have a certain point in time and we want to see if our system is still considered okay, we choose this point in time, for example, normalized time point 4 here, and we see we get this range for the survival probability for our very rough model, which is very fast, of course. If this is sufficient to make a decision, we are fine. We can still make the decision, although our model is very rough, since we cover all the epistemic uncertainty in the model prediction here. And at the same time, if this uncertainty is too large, we can say, okay, then we need to go back to our system and model this more in detail. When we model the system more in detail, then we have a smaller amount of epistemic uncertainty here. So that way we would reduce the bandwidth of this response of the survival function. And that would basically help us to adjust the model detailedness up to that kind of degree which we need to make a decision, and not up to a degree which is just possible, but maybe not needed. So then we can use a kind of relative importance index in order to see which component in the model brings in most of the epistemic uncertainty at which point in time. And this helps us to tell us, okay, which component, which of these hypercomponents should we model more in detail in order to shrink down the epistemic uncertainty then for decision making. So that way we can go step by step to come up with a model which is uncertain, of course, which reflects epistemic uncertainty, but which is only as precise as necessary to make decisions and not wasting resources and still being efficient in order to produce quick results. So this is what we tried for infrastructure systems like metro system of Shanghai and also metro system of Berlin, which we analyzed with different setups of this kind of model. So the other thing is we need to look at our resilience. So we need to think about how to address economic aspects and customer requirements. So if we have a breakdown of our system, if we have a disruptive event, we need to recover our system. So the question is, what is the target quality for our recovery? So should we come back to full service of our system, or is it okay to recover it to 90%? So how much time should we spend? How much time do we actually have to recover our system? How much should we invest for the recovery, and in which part should we invest this? I mean, this is an economic decision. Resources are limited, in particular economic resources. We may have a limited budget, which is available quickly, but then we need to allocate this in an optimal way. And the question is, what kind of technology or which kind of process should we use for the recovery? Of course, we can rebuild something, we can replace something, we can do some temporary structure and these things. So the question is, which technology and process to use? In order to answer these questions, we combine our systems model, which tells us something about the reliability of our system, with a resilience-based lifecycle management approach. So we borrow simply this concept here, which everybody, I guess, knows, for characterizing resilience. So that means we have our reliability of our system, then we have a disruptive event. So the reliability goes down or the performance goes down. And then we have the recovery phase bringing back our system to a certain level of performance or reliability. So this is now just a very simple concept that we are using conceptually to combine this with a systems analysis in order to quantify now resilience in relation also to economic aspects. We use a resilience metric from literature. So this is not our invention. It's just taken from a paper, expressing resilience as an expectation of a stochastic process. And that stochastic process is basically a ratio of an integral over the performance of the system with respect to the target performance of the system over time. So how we quantify this, that is done then in the systems analysis part. And then this expectation tells us what the resilience is. So now we want to include the setup of our system in terms of economic aspects and in terms of features of the systems that we can influence with some investment. So we are using an adapted systemic risk measure, which we borrow from financial mathematics. So financial mathematics, they look at these things from an, for example, insurance perspective, and they think about what is the financial risk of failing and how much should we invest in which part of in the financial market in order to come up with a, let's say, required performance of our financial system. So we borrow this kind of concept and say we express basically the set of feasible solutions of our system in terms of Y, which is the system performance, and K, which is the basic system properties. And then we include also additional system properties, equipment, which is called endowment. So that is an investment which can be made in order to improve our system. So that can be an improvement in terms of improve the robustness of our system in order to make it more robust against disruptive events. Or it can also be an investment which is then done after a disruptive event to bring back our system to service. And that leads then to possible options for recovery in relation to a, let's say, set of options that are feasible, which bring up our system to a certain target level of performance, and this related to some financial aspects. So the problem is then, since we have really many options then for this kind of recovery and investment, this comes to a multidimensional selection problem. So here we have this selection, here we have an illustration of this selection problem, saying that we have 4 component types, C1, 2, 3, and 4. And for each component type, we have a certain quality level to which we can bring this up, for example, after a disruptive event. So in this example, we see component type 3 is the most important one, which controls the performance of our system most effectively. So and that needs to be brought up to, let's say, quality level 15 in this case, in order to make our system, let's say, or in order to bring up our system to a certain required performance again. So, but this is still a multidimensional decision problem. So what we can then do is first reduce this multidimensional search space by, let's say, monetary and technical restrictions. So not all the technical options are available for each and any recovery in any case. So we have technical restrictions, which are only available because technical equipment may not be available and these things. And some technical procedures may not be possible for certain places and these things. So that would reduce the search space. And the other reduction is the monetary aspects, so available budget and these things. So the search space is then reduced to still quite a large number of options. So then we have the customer requirement or customer desire, where people say, okay, I would like to bring back my system to this level of performance or that level of performance, and then still have these monetary aspects. How much would I pay for what kind of recovery level? So we have options which then come up as a reflection in the survival probability of the system. So for each of these options, we can then calculate the survival probability over time based on the concept of survival signature. And then we can basically see what is the outcome for what kind of option for the recovery and what would be the result. So we have a minimum requirement, we have the options, we have a customer desire, and we see which recovery option would lead to the best result in terms of the survival probability. And that includes then cost-effective recovery solutions and stakeholder desire, and all these things can be implemented here. At the same time, we do not only want to come up with a result in terms of best performance of the system, but we also need to look at the remaining epistemic uncertainty. So it might be that we come up with an option where we say, okay, this option looks the best in terms of the, let's say, absolute quantity of the reliability of the system. However, that option may be related to a large epistemic uncertainty, because that may be sensitive with respect to, let's say, the epistemic uncertainties in the recovery process. So that, for example, we have an option to recover a system, but this recovery process that we select may lead to a very good result, but we need very, very qualified people in order to do that. If these qualified people are not available, that includes a lot of epistemic uncertainty in the quality of the recovery. So that would then be reflected in the large epistemic uncertainty in the survival probability. So we do not only look at the level of performance that we may reach with the option for the recovery, but also at the same time at an option for the recovery which is robust with respect to epistemic uncertainties, leading to a smallest possible range. So we need to look at both aspects at the same time. So, and that has been used for recovery options for the metro system. For example, we tried this on the metro system of Berlin. So we looked at the performance of the metro system in terms of network efficiency. And we said we characterize two types of stations in this network, large stations and small stations, small type 1, large type 2. And we have two items here that we consider, which is the robustness of the metro station. So this is the upfront investment. How robust should the metro station be made with respect to disruptive events, or let's say sensitivity with respect to disruptive events? And the recovery improvement of the station means the time to recovery after its breakdown. So we have these two options to invest, and they are related to some optional investment, which can be then covered by some equations and some estimates of cost for the recovery, some estimates of cost that need to be needed to make them more robust, and these things. So, okay, these are basically assumptions for just academic example. This is not realistic numbers in relation to a real case. So, however, it shows that this method can work. Then we can have this kind of options here in the grid, robustness of station type 2 versus robustness of station type 1, small ones, large stations. And then we have a kind of grid search method in order to find the best option in terms of cost for the potential investment, in this case, for the robustness of the stations. And here we found out that the robustness of small stations is actually more important for resilience compared to the robustness of large stations. And thinking about this result tells us that it's actually quite intuitive, because the small stations, they have only one line. And these lines may go far outside the city. So if we have a collapse or breakdown of a small station, it would cut off a line completely, which is coming from outside the city. So it would cut off a whole part of the city. Versus when we have a collapse of a larger station, then we may have only a shutdown of one of the lines, and we can still reach the station with a second line. So that is why the robustness of the small stations is more important. So in total, I think the idea is that the functionality-based systems modeling can lead to reduced models, which are really focused on the key features for efficient analysis. The survival signature can facilitate some non-intrusive simulation-based efficient and flexible systems reliability analysis. And imprecise probabilities can capture uncertainties comprehensively and also facilitate a reduction of the modeling. So we can, with this model, we can basically use, or let's say, address this kind of balance between model detailedness and uncertainties, epistemic uncertainties. Also, using this concept, we can say, we can play across this range of options, this range of models, and see what is the worst case in terms of probabilities. So we can also identify kind of worst case scenarios within this range of models that we consider. A resilience analysis based on a systemic risk concept gives us an opportunity for a multidisciplinary framework for multi-criteria decision-making. And all this kind of stuff together can have general applicability and transferability to other fields. So we also used this kind of concept not only for infrastructure resilience, but also for the repair and maintenance of aircraft turbines. So in overall, I think this concept can help to let's make us available for an efficient and realistic reliability analysis of complex systems and help us maybe to come up with an improved design, performance, and reliability of complex systems. So as I mentioned, this presentation was only conceptual, not too much in detail. And this is actually at the very beginning of some research. So there's still a lot to do. So I may not be able to answer all the questions in very detail, but I hope I can answer all the questions, at least conceptually. Thank you very much.
Thank you, Professor Beer, for a wonderful presentation. Yes, as you mentioned, the infrastructure systems are complex. So starting from complex systems, you introduce the reliability to the resilience-based maintain and upgrade of these complex infrastructure systems. Thank you very much. Now it's our time. We have some time for Q&A. If you have any questions, you can raise your hand or write notes to the Q&A session. Any questions from our audience? Please raise your hand and write some questions. Okay. Any questions or comments? Yeah, I would like first, I would like a question about this, today, because of the webinar, you try to give the concept, mainly on concept. But yearly, when we show these infrastructure systems are complex to our governor, they yearly ask me how complex, for our methodology, how kind of a complex system we can consider for the lifeline structure, or both couple the lifeline structure with the buildings, or even to the city scale. They will ask us how complex of our system is. This is the first question.
Okay, thank you very much. This is a very key question, actually, because this relates to what I mentioned about the modeling of the system. Usually, if we try to model these complex systems in a physical way, as we usually do it, then we may end up with millions or even billions of components in these things. So that is actually way too much detail, let's say, because that would take a long time for the modeling, and it would give us a lot of detail then in the analysis, which we may not even need in order to make decisions. So that's why I said we may not model the system in a, let's say, traditional physical way, but in a functionality-based way. So that means we look at certain features of the system which we can describe with a kind of input-output relationships out of the whole model, which do not need the physical modeling of the whole system. But we try to build a kind of systems model as a surrogate representing the key features of the complex system. So we bypass actually the physical modeling of the complex system by putting up, let's say, very rough, very simple, actually, surrogate, just representing the key features or the key dependencies in our system, which we need for decision making. So for example, we did this for a maintenance of aircraft turbines, and we tried to model the aircraft turbine as a physical model, and that failed because it's way too complex and takes too much time. It needs too much information. But in the end, we were actually interested only in the dependency between the roughness of the plates and the compressor versus the performance of the engine. So we said, okay, we have some key features in the CFD analysis, which we can, let's say, we can do a very rough CFD analysis, which tells us about this dependency. at the same time, we have measurements for the aircraft turbine, pressure ratio and these things between the roughness of the surface of these blades and the performance of the engine. So we combined, also we put up basically a sensitivity analysis based on CFD analysis and calibrated this based on data, measurements from real aircraft. So that has led to a very small scale systems model, just representing this input-output dependency. And based on that, we were able to come up with survival functions, basically telling us how long can this aircraft fly until we reach a certain, let's say, minimum performance of the aircraft, so that it needs to come for maintenance. And then at the same time, use this model also to say which part of the system is the most critical one to look at for maintenance and repair. So that means that we don't work with a full model for the whole complex system, but we find a representative model, a small scale representative model, functionality based, just giving us the key features. And this representative one can still have maybe 100 or 200 components, which is okay for this kind of modeling. But with the survival signature, I think that is also the limit, so that we can model systems with 100, 200 components, but we cannot go to millions. I think there's no way actually at the moment to come up with a reliability analysis of a system which has millions or billions of components and model this in detail.
Thank you. Thank you. This is very important. The way of thinking changing from traditional physical model to the more focus on functionality, and this is important change and to evaluate the resilience of the complex infrastructure systems. Thank you. And we have a question raised by audience. Good presentation, Professor Beer. I have a question. Did you use some special algorithms to compute the best path, for example?
Yes, this is still under development. So the latest developments we have done was to use basically Monte Carlo simulation to estimate in a targeted way some entries in the survival signature. And then we know that the survival signature is a monotonically behaving function. So we then use these selected points that we calculate as support points for a surrogate model. So the surrogate we are using is radial basis function networks, which give us also the option to estimate the second order properties of the survival signature. So we come up with a surrogate for the survival signature based on only estimating a very few points with Monte Carlo, and we include also the sampling uncertainty in this estimate. So that is what we are doing at the moment, and that has led to a, let's say, this enables us to solve problems with a few hundred components.
Okay, thank you very much. And also, I haven't any question from the audience. If no, I will continue my questions. Okay, one more. Okay, thanks a lot. And Quincy said, a question from WeChat streaming. My main focus is on the reliability of mechanical structures. I have read some literature which includes structure and reliability analysis problems with multiple failure modes, defined as structure system reliability analysis problems. Some scholars have defined this type of problem as system reliability problems, but there are also some literature that distinguishes between structure system reliability analysis problems and system reliability problems. This literature believes that structure reliability analysis focuses more on the statistics of failure data. This makes me a bit confused. Can you, may I ask if machine learning may be incorporated to the modeling process of you may already use the method? So those questions, one about the confused of failure data for in the structure reliability analysis, the other one about machine learning, please.
Okay, I mean the failure modes I think is one problem. I think usually we look at one failure mode and then evaluate that, but it's also possible to look at several failure modes at the same time. I mean that's possible, but I mean okay, that's then a serious system or something like that. for which we have approaches that we find in literature. I think the more important thing is the other point you raised with the machine learning. I think we should be a bit careful with that. I mean, machine learning cannot do everything, but it can help us a lot. In particular, machine learning can help us to analyze data and to find patterns in very, let's say, high-dimensional and complex data. So the way forward is to combine the physics-based modeling or the functionality-based modeling with some data. So I think to put up a functionality-based systems model and then do some model updating approach based on data, that is a good pathway forward. And even finding the surrogate kind of automatically, that can be done with machine learning methods. I mean, that is what we are actually doing when I say we use radial basis function networks as a surrogate for the survival signature. So we combine basically these two things. But I would say to use machine learning alone, we should be very careful with that, because that could lead to some wrong results. Because I mean, the machine learning tools cannot reflect the physics without any kind of input from our side. But when we have some idea about the physics behind, then we should use this knowledge as an input also for the machine learning tools. I think that is something very important, that this kind of stuff goes hand in hand. The other problem is with the machine learning, we should be aware that these machine learning tools can do a very good interpolation and a kind of pattern recognition, but these tools cannot do an extrapolation. Extrapolation needs physical knowledge about the system. But when we use the physical knowledge, for example, with physics-informed neural networks and these things, then we can also use these tools for, let's say, at least a kind of limited extrapolation, which is then based on the physics together with the, let's say, learned behavior of our structures or systems.
Yeah, thank you. Thank you, Professor Beer. And I think Xiaoyi raised his hand. Let me see.
Yes. Hi, Professor. Can you hear me?
Hey.
Yeah, Professor, thank you for the wonderful presentation. As you have mentioned, that the inference structure is very complex. So my question is that I always have this question when I do my research. Once we have a certain resilient assessment of the inference structure based on modeling or algorithms, how can we make others believe or have confidence on our results? Do you think it is important to conduct some level verifications of the results of this very large scale of assessment?
Okay, I mean, validation and verification is something very important. I think what we need in particular, if we go for functionality-based modeling, is data. So we need observation data. And I think our infrastructure is actually very good for giving us these data. So I mean, we can have sensors, we can have cameras, and usually we have already cameras in our infrastructure. So what we need is basically access to this kind of data in order to have, let's say, a basis for validation and verification. I think that is basically an open question also at the political level, if we can have access to this data. But I think this is very important. At least we should have access to, let's say, some of the data to do this. But that is something which is very important. So I would not recommend to go with a model which is just based on, let's say, some initial idea and not verified by data. So that's a very fundamental thing.
Okay, thank you very much.
Yeah, thank you. And let me see. Thank you. Okay, so that's yeah, I think that's the notes about appreciate for your responses. And also as somewhat, oh, one more question from the audience. Let me continue his question first. Hello, Professor. Thank you very much for your presentation. I have a couple of questions. How is conditional probability density function determined in your method? And can your method handle problems with a small failure probability?
Okay. The conditional probability that I mentioned is the one which comes out from the survival signature. So that is based on a combinatorial problem that we calculate for L out of M components working. So in that combinatorial problem, we solve with a surrogate with the rated basis function networks and even crude Monte Carlo for estimating some support points for the surrogate. So that is basically automatically a conditional probability given that L out of M components are working. So the small failure probabilities actually come in with the survival functions. So with lifetime distributions. So basically lifetime distributions are multiplied with the survival signature, and we sample from the lifetime distributions then and multiply this with these conditional probabilities. And for this sampling, we can also, let's say, have very small failure probabilities. That's perfectly okay because this kind of approach can be combined with efficient sampling concepts, like, for example, a subset sampling or importance sampling that can be combined. And so it's totally feasible also for calculating very small failure probabilities.
Mm-hmm. Yeah. Yeah. And also there's a question raised by Ali. Is it possible to make it flexible for every country and represent it through another study?
Yeah, I mean, why not?
Yeah, that's a methodology, so which can apply to any country. You know, this the concept that what we call it conceptual is.
It's technical development.
Yes, thank you, Ellie. And also, okay, and if no question, my further question, you know, recently I read references about intelligent computing. This is one way. The other way is to use a methodology, you know, we loved, like a reliability from the point of functionality. So you think, what's your opinion if we have intelligent computing to help us to calculate the complex infrastructure systems for our city? You know, can we in the future to combine both the algorithms by the intelligent computing and our, you know, reliability analysis from the functionality point of view? What's your opinion for the future directions?
No, I think so. I mean, I would never say that we should only go in one direction. So if we have these options, if we have technologies available, we should definitely look at these technologies. We should not disregard one or the other. And I think each technology has certain features, certain advantages, and certain disadvantages. And in most of the cases, I would say a clever combination of technologies combining advantages is always a good idea. So in that regard, I would say, yes, of course, we should look at a possible combination, but we should be careful to combine the advantages and not combine the disadvantages.
And that will be raise another, you know, question about reliability of the disadvantages and the advantages of the results, right? Okay, so it's almost time. Let me ask our audience again. Any questions or comments from our audience? If no, please join me to thank you, Professor Beer, for his wonderful presentation. Thank you. Thank you very much. Thank you.
Thank you very much.
Thank you. And we look forward to your participation next time about the webinar for Journal for Resilient Cities and Structures. Thank you very much.
Okay, thanks very much.
Thank you. Hi,
thank you.
Hi, Quincy. Thank you. Hi, Quincy. Are you there?
Yes. Yes, so for the audience, our recording and slides will be live soon on the journal website. So if you want to, including the previous webinars, so if you want to look at the videos and slides from the previous, please get access to the journal website that I just shared.
Yeah.
Thank you for your participation. Thank you for the wonderful presentation, Professor.
Hi, thank you. Thank you, Professor Beer. Yeah, please, yeah, hi, please keep contact if you visit Tongji University. You are our podcast professor. Please kindly contact us. Okay, see you.
Thanks very much. See you. Bye.
Okay, bye. Take care, everybody. Bye. Thank you.